In this video, we're going to be looking more in depth at the water cycle, and we'll also be looking into something called residence times. Residence times tells you how long will an atom of a particular element, a chloride anion, a sodium ion, a carbonate, will spend in the ocean. And the amount of salt dissolved in a unit of volume in ocean water is roughly constant. That means the elements that go in also come out, and we use residence times to work out how fast those processes happen. A residence time is defined as the amount of a particular element in the ocean divided by the rate at which the element is added or removed from that ocean, from that water body. So residence time, which usually is we use the letter tau to call it, is the amount of an element in the ocean divided by the output input rate. How fast is it added, removed from the ocean? You have what we call conservative elements, which tend to have constant concentration. So some, for example, chloride ions or sodium ions, sulfates, etc. And also some minor elements like bromine, strontium, carbon or fluorine, which have a more or less constant concentration in an ocean. And then we have what we call the non-conservative elements that have a more fluctuating concentration, although we will see it's still a very large residence time. And typically the nutrients like nitrogen or phosphorus, or dissolved gases like CO2, for example, or oxygen, and also some trace elements and organic compounds. What does determine the residence time of an element? The one that will hang around for longer in the ocean, and the ones that are actually more faster removed in and out of the ocean? Well, it depends on its chemical activity. More chemically active elements will tend to react and move out of the ocean and then go back in again at another time. And we have looked into this, if you remember, when we were looking at carbonate equilibrium. And in the first session we did in this module, I was discussing the fact that you can have CO2 in air, and it gets dissolved in water, and it has acid-base processes, and sometimes that CO2 in water will become the ion carbonate, and then it might find some calcium ions and precipitate as calcium carbonate and become solid. And so that's the type of things, that's the type of process, chemical processes, that determine whether an element is going to hang around in the ocean for a very long time, or if it's going to move out in and out of the ocean at a faster rate. As you will see, when we talk about faster and slower rate, we are talking about quite a large number of years. So you've got the conservative elements that spend hundreds of thousands or dozens of thousands of years in a water body, and the non-conservative elements which move in and out of the water body at a faster rate, but even so, considerably slow by human measurements, 200 years in the case of iron. You can also look at residence times when you are looking at a water molecule and how many years or that water molecule will spend in a particular part of the water cycle. So this is a different version of the water cycle. It's slightly more technical than one I showed you in a previous video. So you have a certain amount of water in the atmosphere, a certain amount of water in the oceans, and a certain amount of water in land, continents, lakes, rivers, ice, groundwater. And there's a certain amount of water in the biosphere, in the plants. And you have an exchange between the atmosphere and the oceans, for example. So you have the process of evaporation from the ocean to the atmosphere, and the process of precipitation from the atmosphere back into the oceans. And those are the fluxes, the kilograms per year of water that come, in and out. You also have a process of evaporation and precipitation in continents, and you also have a process of transpiration. You have an exchange between the water in land and the water in oceans, the water in sea. And you also have an exchange between the oceans and the land into the biosphere, the uptake of water from the plants and the process of photosynthesis, and from the biosphere into the atmosphere. So the total water resources stay the same. There's only a certain amount of water on Earth. Where it is at any given time is determined by this water cycle. So now I'm going to ask you to calculate what would be the residence time, tau, of water in the atmosphere. So the residence time of water in the atmosphere would be how much water there is in the atmosphere, what you call in the previous slide steady state, and the flux, the kilograms per year of water coming in or out of the atmosphere. So go back to this slide, stop the video now, and calculate the residence time for water in the atmosphere. So stop the video now. I hope you stopped the video and had a go at trying this exercise. So what is the residence time, tau, of water in the atmosphere? Well, it is the amount of water in the atmosphere divided by the flux, the amount of water coming in and out. So if I go back to this slide, I know the amount of water in the atmosphere, 1.3 10 to the 16 kilograms. And that is, I need to divide that value by the amount of water coming into the atmosphere. So what do I have here as values for water coming into the atmosphere? Well, I've got the evaporation value from oceans into the atmosphere, and I also have the combined values of evaporation from land to the atmosphere plus transpiration, which is from the plants into the atmosphere. So 4.23 times 10 to the 17 plus 7.29 10 to the 16. That is give or take 4.96 10 to the 17, which is where I got from, and that gives me 0.0262 years, which is give or take 9 to 10 days. So that would be the residence time of water in the atmosphere. This is just an example of typical residence times of water resources, and they are variable. For example, here we've got atmospheric water, which we calculated, yes, around 10 days, a week and a half. You've got biospheric water around a week. You have soil moisture 2 weeks to a year. Then you have things like oceans and seas, which have a typical the residence time of 4,000 years. And then you've got some interesting ones like groundwater or ice caps, glaciers and permafrost that have, as you can see, quite a peculiar, quite a wide range of residence times, because it does depend that the groundwater, is that groundwater being exploited, or is it just left alone? Does it have any way to connect outside that groundwater reservoir? So 2 weeks to 10,000 years, depending on specifically the water reservoir you are looking at.